that derive expressions for number of electrons available. So, and what is the formula you have? We have seen n is equal to nc into exponential of minus ec minus ef by kt. Similarly, for holes, we have p equal to nv into exponential of ef minus ev by kt. We have seen the energy band diagrams also. So from the energy band diagrams, we could deduce these expressions. And we have also discussed about this effective mass concept of effective mass of holes and electrons. And we have seen that in case both the effective mass of hole and electrons are equal, then Fermi energy level will be exactly the average of your conduction band energy level and valency band energy level. EF is equal to EC plus EV by 2. Or otherwise, in case the temperature remains at absolute 0 Kelvin, then also irrespective of this effective masses, the Fermi energy level will be the exact average of your EC and EV. Later on, we have seen this mass action law. So what is mass action law? N into P equal to Ni square. We have also derived an expression for this Ni square. And we have also defined a term called energy gap. So energy gap is nothing but uh, the differences, the gap between your conduction band energy level and the valency band energy level. This is your Eg. This Eg, we have seen that it is depending upon temperature. It's clearly depending upon temperature. Eg is equal to Eg naught minus beta into T. Okay. Now, in the last class, I hurriedly introduced this extrinsic semiconductors. So today we will be dealing with this extrinsic semiconductor. Later on, we will start the concept of a p-n junction diode. So in the extrinsic semiconductor is nothing but a intrinsic semiconductor, intrinsic plus impurities. The process of adding impurities is known as doping. So doping, the process by which we are going to add the impurities. Okay. And then first we have two types of impurities. So one is a pentavalent impurity, and then we have trivalent impurity. So first, if we are considering a pentavalent impurity, so pentavalent impurities are like antimony, phosphorus, and arsenic. Okay, so when you have such kind of impurities in very small quantity also, they're going to replace the germanium atoms. So if you see this crystal structure now, so in place of germanium, a antimony Sb element atom has replaced the germanium atom. Now, out of the 5 valency electrons of the antimony, 4 of the electrons are forming the covalent bonds. And then it has one excess electron. This excess electron is loosely bound by the atom of antimony. Now, it is so loosely bound that even if you are going to give a very small amount of energy, so let us say if for in a germanium crystal, if you are going to provide 0.01 electron volt, or for a silicon crystal, if you are providing 0.05 electron volts, so it is very small quantity, then it is able to get liberated from this atom, and now it will be called as a free Hello. Am I audible now? Yes, right. Okay, fine. So sorry for this interruption because I'm using some two devices, one to write on the PPT and one to talk with you. There's some kind of a delay. So sorry for the inconvenience. So now can stop the typing in the chat box. So where were we? So I was talking about this free electron. So when we are able to provide this 0.01 electron volts in a germanium crystal, then this free electron will be able to occupy the conduction band. So an electron not belonging to the germanium atom, but it is belonging to the donor atom. So donor energy level is very close to the conduction band energy level. It is a donor energy level which is close to the conduction energy level, conduction band energy level. So electron belonging to the donor will be able to reach the conduction band upon receiving this 0.01 electron volt of energy, right? So more number of electrons from the donor atoms will be able to reach the conduction band. So once this conduction band is occupied more by this donor energy atoms, then what happens? So electrons from the of the germanium belonging to the valency band, they cannot reach the conduction band. So compared to the electrons from the valency band, the electrons from the donor energy level will be occupying the conduction band. So unless an electron leaves the valence band, there is no scope for hole to exist in the valence band. So once an electron leaves the valence band, then only we can have the hole in the valence band. So I can say that, so when you are adding this pentavalent impurity, then I can say that number of electrons in the conduction band is greater than number of holes in the valence band. These electrons, free electrons are in conduction band and these holes are in valency band. So N is greater than P when you're adding a pentavalent impurity. So N is nothing but free electrons in the conduction band. There will be more in number. This number is mostly contributed by the donor atoms. So because they are donating the electrons, they are often termed as donor atoms, and this type of impurity are called as donor impurity because they are going to donate the electrons. So here you should also remember that once they donate the electron, they become positive ions. So a neutral donor atom on donating an electron will become a positive ion. So I can say that the charge that donor ion is having is a positive charge. Okay, and because they are contributing for these electrons, then they are also known as N-type because N-type particles are more in number now. N-type impurities. Okay, and then similarly, if we are adding a trivalent impurity like boron, gallium, or indium to an intrinsic semiconductor. So if you take a indium atom in a germanium crystal, you can see that so three electrons are forming three covalent bonds, whereas the fourth covalent bond is not complete. It is vacant because we do not have the fourth electron. Indium cannot provide for the fourth electron. This absence of this electron we are terming as the hole. So when we are adding the trivalent impurity, we are getting more number of holes. So if you go for this energy band diagram, the acceptor atom energy level will be close to the valency band. It is far away from the conduction band. So this is the acceptor level energy level, acceptor ion energy level. And now whenever you have this hole, this is an empty shell, right? Some of the electrons from the germanium will try to recombine with this hole. Okay, so what happens? electrons from this valency band, electrons in the valency band will be reaching the acceptor energy level. Okay. So in order to form the covalent bond. So it's a recombination. So for these electrons, reaching the conduction band is more difficult. Reaching the acceptor energy is much easier. This is also a stable state. Okay. So what happens? So once these electrons leave this valency band, then a hole is created in the valency band. Okay. So now more the electrons are in the acceptor energy level. So most of the electrons will occupy the acceptor energy level instead of occupying the conduction band. So number of electrons in the conduction band are less. Number of electrons in the acceptor energy level are more. Even though they are reaching the acceptor energy level, they are not free electrons because these electrons are now joining this hole and now are the part of a covalent bond. Okay, now they are not your free electrons anymore. They cannot contribute for conduction of electricity. Okay, so this results in we are having more number of holes in the valency band and less number of electrons in the conduction band. These holes are in valency band. These holes are formed because electrons have left the valency band and occupied the acceptor energy level. And similarly, free electrons will also always be in the conduction band. So compared to the electrons in the conduction band, most of the electrons are be existing in the acceptor energy level. Also, this acceptor energy level is very close to the valence band energy level. Okay. So because of which P is greater than N in Na, you are adding a trivalent impurity. Okay. And the effect of this impurities are into such an extent that even if you are adding one part in 10 power 8 parts, okay, it's something like 1 by followed by 8 zeros. Even if you're adding to this small quantity to this fraction also, then also the conductivity of the germanium will be improved by a factor of 12. So you should be understanding the effect of this donor impurities or your acceptor impurities. So adding an impurity, the conductivity is going to increase. Okay. So in an n-type semiconductor, we have the electrons in large number and they are called majority carriers. And the small number holes are called as minority carriers. In a p-type material, so p-type material is a material where you're adding trivalent impurity. Okay, when you're adding trivalent impurity, so you have more dominant holes. So that's why it is called as p-type material. They are the majority carriers. They have small number of electrons in the conduction band, which are called as minority carriers. Because these ions are accepting the electrons from the germanium atoms. Because they are accepting electrons, they are called as acceptor impurities. Acceptor impurities. And because they are accepting the electron, they become charged. Acceptor ions will become negatively charged upon receiving the electron. Whereas you can see that donor atoms have become positively charged upon donating the electron. Okay, that's the major difference between these two. Now coming to the charge densities. Now you know that whether it's intrinsic semiconductor or extrinsic semiconductor, it is electrically neutral. So first we shall balance the positive charges and negative charges. So in electrical neutral material, we have positive charges is equal to negative charges. Okay, so positive charges are contributed by holes and negative charges are contributed by electrons if it's a intrinsic semiconductor. In addition to that, we have positive charges as donor ions and negative charges as acceptor ions. Because donor atoms are giving away the electron, they become positively charged. Whereas acceptor ions are taking the electron, they become negatively charged. So this equation Nd plus P equal to Na plus N. Now if we consider only N-type material, in N-type material, what happens? In N-type material, we have only donor type of impurities. We do not have any acceptor impurities. So this Na is equal to 0. And then also in a N-type material, we have seen that N is greater than P. So I can neglect this P also. Now I can write that N is nearly equal to Nd. So in a N-type impurity, number of free electrons is equal to number of donor atoms. This is the concentrations. Okay. So in N-type material, free electron concentration is approximately equal to the density of your donor atoms. And then from this equation, you can write that you already have this mass action law, N into P equal to, or P into N is equal to Ni square, right? Now if you are writing in place of N, if you are writing Nd, so it will be P into Nd is nearly equal to Ni square, or P is nearly equal to Ni square by Nd. So in a N-type material, number of holes is nearly equal to Ni square by Nd. So because we are calling it for a N-type material, we are giving a small suffix N. So Pn is nearly equal to Ni square by Nd. Okay. So similarly, if you are considering for a P-type material, in a P-type material, there will not be any donor atoms. Okay. And also P is greater than N. So if you again replace in this equation, what happens? P is equal to Na plus N, and P is greater than N. So if you are neglecting this, it is as if number of holes is nearly equal to number of acceptor atoms. So we are giving a suffix in a P-type material Pp. Pp is nearly equal to Na. So again, if you replace here, N into P equal to Ni square, the mass action law. If you replace Pp as Na, so Np, so Np means number of free electrons in a P-type material into Na is equal to Ni square. From this you will get Np is nearly equal to Ni square by Na. Okay, these are free electrons in a P-type material. So these will be small in number. These are minority carriers. These both are. So holes in a N-type material and electrons in a P-type material are minority carriers. So these are the minority concentrations. Whereas these are the majority concentrations. So N is nearly equal to Nd. And then you have P is nearly equal to Na. This Nn, this Pp. In case if you are not hearing my audio, you can please let me know. Okay, you can unmute and tell me in case my audio suddenly goes off. Okay, now we shall look into the Fermi energy level. So as we have already seen that Fermi energy level will depend upon the temperature and the impurity concentration, because we have derived an equation for EF earlier. We have seen that at absolute zero, your EF is equal to EC plus EV by 2 at T, either where T is equal to 0 Kelvin, or if your effective mass are equal, MP is nearly equal to Mn in an intrinsic semiconductor. Now we shall see what happens to this Fermi energy level in a extrinsic semiconductor or impure semiconductor. Okay, in a N-type material, what happens? So in the N-type material, most of the electrons are occupying the conduction band. Free electrons are in the conduction band. Okay, so Fermi energy level is a measure of the probability of this electrons, right? So as the most of the electrons are moving towards the conduction band because of the existence of this donor atoms, the Fermi energy level will not be at the exactly half of the ECN plus EV. Instead, it moves towards the conduction band. So in this diagram, you can see that the Fermi energy level has moved towards the conduction band. Similarly, if you take a p-type semiconductor, in a p-type semiconductor, most of the electrons are occupying the energy levels of your acceptor ion. Okay, so most of the electrons are staying at this energy level, at the energy level of your acceptor ion. So what happens? Instead of being at the exactly at half of your EC and EV, the Fermi energy level will be brought down towards the valency band. Okay, so in a n-type material, your Fermi energy level will be somewhere slightly below your donor energy level, but above your average of EC plus EV. Okay, so I can simply write, if I even if I do not know anything, I can simply write that in n-type material, for n-type material, EF will be equal to EC plus EF by 2 plus something, because the level has now increased some, let us say some X value. For a p-type material, similarly I can write that EF equal to EC plus EV by 2, because it has now got down in a p-type material. I can write some value minus. So it is, so EF will be above this average of, sorry, EC plus EV by 2, and for a in a p-type material it will be below this average of EC plus EV by 2. Now let us check the exact quantitative equations. Now what we need to do is, we need to go back to the equation Nn is equal to Nd. So here we have already written Nn is equal to Nd. So from this, in this equation, what we are going to do is, we are going to replace the equation for N. We already know that the number of free electrons is given by the expression Nc into exponential of minus of Ec minus Ef by kT, which we have derived in the last class. Okay, now we are replacing this equation over here. Now Nd is equal to Nc into exponential of Ec minus Ef by kT. If we rewrite this expression and take logarithms, then we'll get Ef is equal to Ec minus kT into log n Nc by Nd. Okay, simply what we are doing is, we are taking this Nd to that side, and we are taking the exponential to the left hand side. That makes exponential of Ec minus Ef by kT equal to Nc by Nd. And then we are taking logarithm. So Ec minus Ef equal to kT log n Nc by Nd. And then if we bring all this term to this side, we will get this expression. Okay. Similarly, we can do it for p-type material also. In p-type material, we have to replace the expression for electrons p. So I think the slide is not changed. Please check if the slide is changed to the p-type material or not. Please let me know. I think the screen has frozen. Hello, is the slide is showing towards any p-type material, or still it's in the Fermi level slide? (42) has frozen. No, sir. Okay. It has not changed. Okay. I'll reshare. Just a moment. Teams is freezing sometimes. Okay, I think the screen has now changed. So like we have done for in n-type material, we have done n is equal to nc exponential. The same similarly, we are writing for a p-type material. We'll write p equal to nv into exponential of minus ef minus ev by kt. Now similarly, like earlier class, we'll get an expression for ef. Ef is equal to ev plus kt into log n nv by na. So it means that Fermi energy level is just slightly above the valency band in a acceptor, or when the acceptor impurities are present. Similarly, if you see this expression, you can see that Ef is called Ec minus Kt into log n Nc by Nd. It means to say that your Fermi energy level in an n-type material is slightly below your conduction energy band. Okay. So how much it is lower or higher will depend upon this concentrations of donor impurities and acceptor impurities. So if we write both this expression, Ef equal to Ec minus Kt into log n Nc by Nd, and then again one more expression, Ef is equal to Ev plus Kt into log n and C by Nd, right? Now if we add both these expressions, what you are going to, sorry, this is Na. If you add both this expression, you will be getting 2Ef is equal to Ec plus Ev, and then so instead of minus Kt, I will be writing everything in terms of plus only, plus kt log n, because if you take minus to the inside the logarithm, it will become nd by, it will be inverse. Okay, and then again adding this, we'll get nc by na. Just let me see, it's nc by nd, and here we have ef is equal to ev plus kt. Okay, it is nd by nd, and then you have nc by, so this is a nv by na, nv by na. Okay, now in this case, in case if you are taking a situation where number of acceptor impurities is equal to number of donor impurities is equal to, let us say, some n, so I will simply write n impurities. In that case, what happens is nd and na will get cancelled, so you are left out with 2ef is equal to ec plus ev plus kt log n nv by nv by nc. Okay, so ef is equal to ec plus ev by 2 plus kt log n nv by nc, kt by 2 log n nv by nc. The same thing you can rewrite as ec plus ev by 2. Instead of plus kt, you can also represent as minus kt by 2. Only thing is that if you are changing the sign over here, the logarithm terms will also be interchanged. It will become log n nc by nv. So this is the final expression that you are getting over here. So if you see this expression, it is very much similar to that of a intrinsic semiconductor. So from this I can say that if the number of donor impurities is equal to number of acceptor impurities, so in terms of concentrations, then your extrinsic semiconductor is as good as your intrinsic semiconductor. So it behaves as like a intrinsic semiconductor only. The Fermi energy level is not going to change if you are adding equal number of impurities on both sides. So with this, we are coming to the end of the review of semiconductor physics. Now we'll be dealing with the P injection diode. So if you have any doubt till now, you can raise your hand and you can unmute and answer. It's 2:20 now. So if you have any queries in the review of semiconductor physics, either in the intrinsic or in the extrinsic semiconductors, if you have any doubts, you can ask me. So what we are deduced is that Fermi energy level is going to vary in the n-type material and the p-type material. In n-type material, Fermi energy level is going to shift towards conduction band, and in p-type material, it is going to shift towards valency band. Okay, and then if the number of impurities are both equal, so N is equal to Na, in that case, Fermi energy level will be very much similar to that of a Fermi energy level in a intrinsic semiconductor. And then if you have any doubts, you can unmute and ask. I'll give you 2 minutes of time, or otherwise you can raise your hand and then you can type your query in the chat box. Please unmute and ask. Otherwise, I will randomly call some people and I will ask you to answer the questions that I shall do then. First, I'll ask someone from the A section. So, 227, Davala Srinivas Rao. 227. Has to unmute and answer. Yeah. You can unmute and answer. Allow to unmute. I'm allowing to unmute. 227. So the query for you is, tell me the expression for Fermi energy level at 0 Kelvin. What is the Fermi energy level at 0 Kelvin? You can unmute and tell, or you can simply type in the chat box. Whichever is convenient for you, you can do that. So I'm allowing you people to unmute. So if you're not responding, I'll consider it to be absent in our
Sir.
Yes. Tell me, what's the value of Fermi energy level at 0 Kelvin? So a very simple expression. You not even if you orally you not use any formula, also you can orally tell. So where it will lie? Fermi energy level in a intrinsic semiconductor at 0 Kelvin.
Sir. EC plus CE by 2.
Yes, EC plus EV by 2, correct. Thank you. Okay, next question is for B section student. So let me spin. So 2A5, Mahalakshmi, Kanak Mahalakshmi. 2A5, is she present? 2A5. A5 present or not? A5 is present. I can see her. Okay. Please unmute and answer. A5. For you, you have to tell me. So, an example for acceptor impurity. I think the same questions are already posted in the quiz also. In the quiz that you played in the quiz. Please unmute and answer, or you can, if you want, you can type in the chat box also. I'll even check that. Antimony. So antimony is acceptor impurity or a donor impurity? So I'll again pose this question for someone from section A. So A5 has coded that acceptor impurity is antimony. So Mr. Ramkrishna, roll number 240. Roll number 240. Yeah. You can unmute and answer, or you can directly type. So is antimony is a acceptor impurity or a donor impurity? So what type of impurity is this? Antimony, SB. Donor impurity, right? So 2A5 is wrong. So antimony is a pentavalent impurity. So pentavalent impurities are donor impurities. Okay. Fine. So next we shall move to again B section. Ishwar Akil 73. Ishwar Akil 73. Akil, are you present? If you're present, yes, you are present, right? So what happens to the Fermi energy level when we are adding a n-type impurity? Fermi energy level, will it stay at the EC plus EV by 2, or it is going to shift? If it's going to shift, towards which side it is going to shift? Whether it is going to shift towards the conduction band, or is it going to shift towards the valency band when you're adding a n-type impurity? Forget about the equations. The equations you can derive later and then practice, and then you can remember. Okay, for time being, you can simply answer this question qualitatively. You can answer whether the Fermi energy level is going to shift towards conduction band or towards the valency band when you're adding a n-type impurity. Please answer. It shifts towards conduction band. Okay. Right. Okay, with this I'll end this and I'll be opening the PN junction PPT. So first I'll tell orally and then I'll open the PPT in the meanwhile. So in a PN junction diode, what happens is we have first a intrinsic semiconductor on which one side we are going to have n-type impurity and then on the other side we are going to have p-type impurity. So one side we are going to give donor atoms and on the other side we are going to give acceptor atoms. Okay, so with this what happens, uh, what are the majority carriers in a when you are having a p-type impurity? Someone can answer. I'll call again randomly. A section already over, right? So I'm just spinning. 48. Such a Naveen. 48. You can unmute and answer. So what are the majority
Yes, sir.
carriers when you're having a donor type of impurity?
Electrons.
Okay. When you're having a donor type of impurity, you're having electrons as the majority carriers.
Mhm.
And when you're having a acceptor type of impurity, you have holes as the majority carriers. Okay. And then what is the charge of next question? I'll give it to the B section guys. So 290. Tanmay. Tanmay, please unmute and answer.
Sir,
What is the charge of the acceptor ion? What's the charge of the acceptor ion? Whether it's positively charged or negatively charged?
negatively charged, sir.
Why it is negatively charged? If you're not telling the reason, it means you're taking chances. Either it should be positive or negative. You're telling one of the answers, right? So please let me know the reason behind that. Why it is negatively charged? Why acceptor ion is
Ho-
negatively charged?
Holes are holes are positive, sir. So positively charged, sir.
Just now you told negatively charged. I'm asking about your acceptor ions.
Sir, it's positively charged, sir, because holes are positive, sir.
Holes or positive? I'm asking about acceptor ions. I'm not talking about holes.
Because it attracts electrons, sir.
Okay, once something like when you're at what is the charge of electron? Positive or negative?
Negative, sir.
So when somebody is attracting a negative thing, so what shall it become? When you're attracting negativity, so what will be your charge? Positive or negative? When you are already taken, so you are accepting electrons, right? Acceptor ion accepts electrons. So upon accepting electron, it becomes negatively charged. It is not positively charged. This should always keep in mind because it forms the basics of your PN junction diode. That's why I'm asking you these questions. Okay. So it is not positively charged. It is negatively charged. Okay. Similarly, donor atoms, they are giving away the electrons. They are donating the electrons. So they become positively charged. Okay. Okay, now I'm going to share the screen. So because only 5 minutes are left, I'll just introduce this topic and we'll continue in the next class. Can you see the screen? Is my screen visible?
Yes, sir.
Yes, right. Okay. Are you able to see the PPT? Okay, fine. Now it is visible.
Yes, sir.
So first I will zoom this. So this is a PN junction. Is the image visible to you or it is not visible? Somehow it is flickering for me. Anyways, we shall start this topic from the tomorrow. Somehow my PPT is not loading properly. Okay, so because these things coming to electronics, you cannot physically see them. I should represent them by means of some kind of images. So unless I have a PPT, it will not be easy for you to imagine things. Okay, I will continue this PN junction topic. I will introduce. I will complete most of the PN junction topic during the next upcoming classes. So in the first two classes, we have seen the review of semiconductor physics. Okay, this is the basis for your PN junction diode. I'll start the PN junction diode topic from the next class. Okay, so I'll take the attendance and then you can leave.